Hey there. Tonight, I want to begin with a quiet confession. The map you carry in your head is younger than your bones would guess. And the great joined continent that people love to picture in school books was not the first grand face this planet wore. Long before that famous union of land, before the age of thunder lizards, before forests learned how to whisper in the wind, Earth had already gathered itself into older shapes, stranger shapes, and then let them drift away into darkness again. That is the secret at the center of tonight's journey. The world before that last giant continent was not empty. It was crowded with forgotten worlds. If this kind of slow wandering through deep time feels good to you, do tap like. Do subscribe. Keep this little candlelit corner alive for the next restless listener who needs somewhere gentle to drift. Then let your shoulders sink a little. Let the jaw unclench. Let the room dim around the edges. Breathe in slowly and breathe out like you are setting down a heavy coat after a long day. We are not rushing anywhere tonight. The Earth certainly never did. Honestly, I have always found it strange that we are taught one famous ancient map, as if the story begins there, as if the continents once had a dramatic reunion, and that was the whole trick. It is a lovely picture, I know. South America leaning into Africa like two old neighbors meeting again after a very long silence. North America and Europe hovering close enough to feel familiar. India not yet having made its reckless sprint north. It all feels satisfyingly neat, like a broken plate patiently repaired. But the darker truth, and I mean darker in the soft and ancient sense, not in the loud and bloody one, is that the world we recognize is only the newest mask. Earth has a habit of changing its face while no one is looking. It gathers its lands into impossible unions, tears them open with fire, drowns their edges beneath shallow inland seas, freezes them under ice, bakes them under heavy skies, and then does it again, over and over. A patient old ritual, a planetary compulsion. If you were standing here with me by the fire, I would ask you to imagine a globe in your hands. Not the bright classroom globe with clear labels and cheerful colors. A darker one. A quieter one. One with names rubbed off. Turn it backward through time. The continents begin to move. The Atlantic narrows. The Pacific changes shape. Coasts slide together. Familiar shorelines lose their confidence. Then keep turning. Keep going. The shapes stop being easy to recognize. The puzzle pieces distort. Mountains that do not exist yet rise from vanished coastlines. Oceans close without ceremony. Other oceans open in the dark. Entire worlds arrive and disappear before anything like a bird ever crosses the sky. That is where the real wonder begins. The farther back we walk, the fewer footprints remain. Rocks are not loyal historians. They are melted, buried, crushed, folded, and worn down grain by grain. Old seafloors are pulled into the mantle and erased. Ancient mountain ranges are shaved down until their bones lie exposed. Then even those bones crack and weather into dust. Fossils become scarce, then rarer still, then almost impolite to hope for. Deep time is a room where most of the lamps have gone out. And yet, somehow, the clues remain. Tiny magnetic signals locked inside old minerals. Belts of stone that match across continents, now separated by whole oceans. Chemical traces sleeping in crystals older than most ideas. Fragments of continental crust that survived what should have destroyed them. Scientists gather these pieces with the patience of monks and the stubbornness of detectives. They compare. They argue. They redraw. They doubt. They return. Bit by bit, a lost atlas emerges. And in that atlas we meet names that sound less like geology and more like sleeping kingdoms. Rodinia, Nuna, Kenorland, They sound almost theatrical, and perhaps that is fitting, because each one was once a stage large enough to hold nearly all the dry land on Earth. Each one was real. Each one mattered. Each one changed the climate, the oceans, the chemistry of the air, and the possibilities available to life. And each one, in time, broke apart. Pause there for a moment. That last part matters. Nothing stayed assembled. Not forever. Even the grandest landmass was only a temporary arrangement. Just another long breath in the slow chest of the planet. When that famous later supercontinent existed, Earth already had forests, rivers, insects, reptiles, and the first long shadows of the dinosaur world ahead. But go back to Rodinia, and suddenly the land feels almost bare of everything familiar. No trees, no grass, no bird song, no mammal tracks in soft soil, no flowers opening to the sun. The land was rock and weather and silence. Life lived mostly in the oceans, and even there it was still practicing simplicity. Go farther back to Nuna, and the silence deepens. Farther still to Kenorland, and tiny ancient crustal seeds like and the world becomes so stripped of the familiar that the continents themselves feel like the main characters. They drift. They collide. They crack apart. They carry the entire future on their hard, slow backs, while life, still microscopic for much of that time, clings to coastlines and shallow seas and quietly alters the sky. You know that feeling when you enter an old museum hall and the air seems thicker, as if time itself has settled into the stone. That is the mood of early Earth. Dust, mineral smell, the hush of old rock, holding heat from an afternoon sun. Water sliding across a barren shore without reeds to catch it. Wind moving over naked ground. No buzzing insects. No leaf litter. No hidden animal eye looking back at you from the brush. Because there is no brush yet. Only stone. Only tide. Only the patient rearrangement of land. That is why the world before that later great continent matters. It was not merely an earlier version of home. It was a chain of worlds so different that each one almost qualifies as another planet wearing Earth's name. Let us begin with the simple idea most people meet first. Continents move. That sentence sounds so mild, so harmless. Continents move. It should perhaps sound more unsettling than it does. The ground beneath us feels like the one thing that should not wander. Oceans, yes. Clouds, certainly. Even mountains, if you wait long enough, can be worn down. But the continents themselves, The land that feels final, weighty, dependable. That too is drifting. Very slowly, of course. So slowly that a human life notices nothing but a coastline pretending to be permanent. Yet over millions of years, that slowness becomes astonishing. The land slides. Oceans widen on one side of the planet and close on the other. Mountains rise where seas once rolled. Old shorelines are lifted to the sky. Whole climate belts migrate as the continents shift north and south. And once you accept that movement, another realization arrives almost at once. If continents move, then they have not always been where we found them. If they have not always been where we found them, then our map is only a snapshot. And if our map is only a snapshot, then there were other maps. Many others. Maps no human eye ever saw, but that still shaped the world that shaped us. The old famous supercontinent was one of those snapshots. Not the first. Only the most recent dramatic gathering of land. Before it, other unions had already happened. The planet had practiced this maneuver before. It had already clustered nearly all its land into one immense body. It had already broken those bodies apart and scattered them. It had already pulled oceans open like seams in fabric and then stitched them shut again with mountain chains. There is something almost funny about it. The Earth is like a host who keeps rearranging the furniture while all the guests are asleep, then acts innocent in the morning. We wake up in one arrangement and assume that arrangement makes sense, only because it is the one under our feet. But deep time is not sensible in the human way. It is grand, repetitive, destructive, creative, and wonderfully indifferent. If we condense all of Earth's history into a single day, human beings arrive so late that the metaphor almost becomes rude. Entire continental cycles had already played out long before our species learned to shape a word. Even the age of dinosaurs belongs near the very end of that day. The earlier worlds, Rodinia and Nuna, and those still older fractured beginnings, belong to the long hours before evening, when the stage was being built in slow silence. And what a stage it was. Volcanic eruptions lasting not hours, but ages. Oceans spreading over continental edges and retreating again. Ice advancing into places where ice should not by ordinary intuition exist. Atmospheres thick with gases that would have made the modern sky feel like a rumor. The planet was busy long before it was familiar. I think there is comfort in that. Maybe a strange comfort, but real. The Earth beneath us has survived so many versions of itself. It has been almost entirely frozen. It has been wrapped in greenhouse warmth. It has worn orange skies and blue ones. It has carried barren rock where there are now forests and seas where there are now mountains. It has not always looked hospitable, and yet life persisted, learning the edges of possibility one era at a time. So tonight, as we move farther from the map, do not think of this as leaving the real world behind. Think of it as stepping into earlier drafts of the same world. Versions where the coastlines were still undecided. Versions where the air was still negotiating with microbes. Versions where continents were learning how to gather and split and gather again. We will walk through them slowly, through drifting lands and vanished oceans, through early atmospheres and long seasons of ice, through the bare silence before forests, and the first green pioneers that softened stone. Through ancient seas, crowded with impossible creatures, and through the patient road that eventually led the continents into their later famous embrace. But for now, let the first truth settle into you like low evening light. That great joined land from the old diagrams was not the beginning. It was only one turn of a much older wheel. Before it, the earth had already worn other faces, and those faces, though lost, still rest beneath everything we call home. And once that idea settles, once the familiar map loosens its hold, the next question arrives almost on its own. If the continents were not still, then what moved them? What gathered them? What tore them apart? And what deep, slow engine has been turning under the crust all along? The quiet answer begins beneath our feet, far below soil and roots, below limestone and granite, below every fossil and buried shoreline, in a place no human has ever touched. The earth is not solid all the way through in the way our instincts would like. Its outer shell is hard enough to stand on. Yes, hard enough to build cathedrals on. Hard enough to crack your knee against if you are careless in the dark. But below that shell, deep in the mantle, the planet moves with a slowness so patient it almost escapes imagination. Rock, under enough heat and pressure and time, flows. Not quickly, not dramatically to the eye. No river like water, no obvious rolling tide, more like something half asleep, something thick and ancient, adjusting its weight over millions of years. Heat rises from below. Material cools and sinks. Vast convection currents turn in the deep. And on top of that deep and hidden motion ride, the rigid plates of the crust, each one carrying pieces of ocean floor, island arcs, and continental land like rafts on a black, invisible sea. That is the engine. That is the slow machinery behind wandering continents. When I first understood this properly, I remember feeling almost cheated by ordinary ground. It looked so fixed. Pavement, stone walls, cliff edges, all of it, announcing permanence with such confidence. Yet permanence is only what slowness looks like to creatures whose lives are brief. Give the earth enough time and every border becomes negotiable. Plate tectonics is the name we give to this ceaseless rearrangement, though the phrase itself sounds tidier than the reality. Plates pull apart. Plates scrape past one another. Plates dive beneath one another. New crust rises along mid-ocean ridges where magma wells upward and cools. Old oceanic crust is dragged down into subduction zones and consumed again. Continents, made of thicker and more buoyant crust, resist being swallowed so easily, which is why they survive. Vanda, collide, split, and survive again. Imagine the continents not as immovable masses, but as old travelers. Some move together in temporary loyalty. Some drift apart for ages. Some collide with such force that mountain chains rise like scars. Some spin, twist, or rotate. Some carry fragments of much older continents welded into their interiors, so that a modern landmass is less a single object than a patchwork coat stitched from immensely old cloth. This is why the farther back we go, the stranger the map becomes. Coastlines are not sacred. Oceans are not eternal. The pieces change shape as they travel. sediment builds up, mountains erode away, volcanic arcs are added to continental edges, rift valleys open and widen into new seas. The puzzle never stays the same shape long enough for comfort. And yet there is a rhythm to it. A real rhythm, repeated over immense spans of time. Geologists call it the supercontinent cycle. But if you want the fireplace version, the sleepless night version, the version that settles in the body rather than just the mind, think of it as the breathing pattern of the planet. The land gathers inward. The land scatters outward, then inward again. A contraction, an expansion, a long inhalation of continents, then a longer exhalation of oceans. That breathing has gone on for billions of years. Before the most famous supercontinent, there was Rodinia. Before Rodinia, Nuna. Before Nuna, likely Kenorland. Before that, smaller and more uncertain beginnings. Ancient seeds of crust, like perhaps others whose evidence has been too bruised by time to speak clearly. Every cycle seems to last hundreds of millions of years. Land gathers into one enormous body. Heat builds beneath it. The crust weakens. Rifts begin. The giant landmass tears open. New oceans are born. The fragments drift, rotate, wander. Other oceans close elsewhere. Eventually, the lands meet again in a new embrace. If it sounds almost biological, that is because it feels that way. Not alive in the human sense, perhaps, but alive in process, alive in recurrence, alive in pattern. You might wonder why the continents do not simply keep drifting farther apart forever. It is a sensible question. If they can separate, why not continue separating until the globe becomes a permanent scatter of islands and continents? The answer is wonderfully simple and wonderfully severe. Earth is finite. Its surface curves back on itself. As oceans widen in one region, older ocean crust is often being destroyed in another. Openings and closures are part of the same system. The world has only so much room. Separation on one side of the planet often means convergence on the other. Sooner or later, somewhere, the seas in between begin to disappear. And when oceans disappear, the real drama begins. Oceanic crust slides down beneath continental margins. Volcanic arcs rise. Earthquakes rattle ancient shorelines. Marine basins narrow. Then, at last, continent meets continent. The buoyant crust resists sinking. It crumples. It thickens. Mountains rise. Oceans die. A supercontinent is born not in a moment, but in a long, slow catastrophe. The Himalayas today are one modest example in comparison with the deep past, though modest is not the word one would choose while standing before them. India is still pressing into Asia even now, lifting marine limestone to the roof of the world. Picture that same kind of collision multiplied across larger spans of the planet and carried forward for tens of millions of years. That is how the great continental unions were assembled. Rodinia, around 1 billion years ago, gathered much of Earth's land into one broad body. Nuna, earlier still, seems to have brought together the ancient cores of lands that would later become North America, Scandinavia, Siberia, India, Australia, and others. Kenorland, older again, emerged in a world so early and austere that even the oxygen-rich air we take for granted would have seemed like fantasy. And tiny if the reconstructions are right, may have been one of the earliest enduring continental kernels. Not grand in size, but grand in persistence. A small, hard beginning that may have survived within later continents, like an old family heirloom, stitched into newer fabric. There is something almost tender in that idea. Beneath modern continents, beneath highways and cities and fields of grain, there may still lie fragments of unimaginably ancient land, pieces that were already old before complex life had taken shape. A pebble can be impolite that way. It can look so ordinary while carrying 500 million years more history than your language has words for. Of course, none of this was obvious to human beings for most of our own short history. For centuries, people assumed continents were fixed, as permanent as the stars seemed. Even in the early 20th century, when Alfred Wegener proposed continental drift, the suggestion sounded scandalous to many scientists. He had evidence in the fit of coastlines, in matching fossils, in mountain belts that aligned when continents were brought together. But he lacked the full mechanism. The image was right before the machinery was understood, not until the middle of the 20th century, with seafloor spreading, paleomagnetism, and the deeper acceptance of plate tectonics, did the whole picture begin to settle. Ocean floors turned out to be young compared with continental crust. Magnetic stripes on either side of mid-ocean ridges recorded the creation of new crust. Ancient minerals preserved the latitudes at which rocks formed. The hidden motion of the plates was no longer speculation. The Earth had been caught in the act. I like that phrase. Caught in the act. As if the planet had been rearranging the furniture for eons, and at last someone walked in and noticed the chairs still sliding. The evidence is beautifully stubborn. Matching fossils on continents now an ocean apart. Similar rock layers. Ancient mountain chains, broken and scattered by later drift, but still recognizable when reunited. Magnetic signatures frozen into cooling volcanic rock. Tiny mineral needles holding their old orientation like a memory. Radiometric dates fixing events into a timeline older than ordinary intuition can bear. It is from this quiet accumulation of clues that the earlier supercontinents emerge. Not as perfect certainties, not as crisp maps, with borders like in an atlas, but as reasoned reconstructions. Ghost geographies. Deep time sketches drawn from stone. And each reconstruction carries a mood. Rodinia feels austere to me. A motherland of bare rock and microbial shorelines. Nuna feels older, calmer, almost monastic in its patience. A giant land under a weaker sun, while life keeps to simple labor in the seas. Kenorland feels harsher, dimmer, more hazardous, under a sky still negotiating with oxygen. Feels intimate, a seed rather than a continent, a beginning too small to boast, yet enduring enough to matter. These are not scientific categories. Of course, that is just my fireside way of remembering them. The rocks themselves are more disciplined than my imagination. Still, imagination has its place here. The world before that later famous supercontinent cannot be understood only as a list of names and ages. It has to be felt as recurrence, as motion, as the planet's long habit of gathering itself and pulling apart again. And the gathering mattered. Whenever continents clump together into a supercontinent, the consequences ripple outward through everything else. Climate changes. The interior of such a landmass often lies far from the cooling influence of the sea, which means dry conditions, broad deserts, stronger seasonal extremes. Ocean circulation changes because coastlines and gateways change. Mountain building alters wind and rain patterns. Erosion from those mountains delivers nutrients to the oceans. Sea levels shift. Habitats expand in one place and vanish in another. The cycle does not merely rearrange land. It rewrites the conditions of life. That is why the supercontinent story is not just geology. It is climate history, ocean history, biological history. It is one of the deep structural rhythms of the living world. When Rodinia assembled, the vast interior may have been dry and severe, while coastal margins and shallow seas held the richest microbial life. When it broke apart, ocean circulation changed. Weathering rates changed. The chemistry of the atmosphere shifted, and the world may have lurched toward the great Snowball Earth glaciations. When Nuna existed, its broad, stable platforms likely influenced shallow marine environments for hundreds of millions of years. Even earlier assemblies may have affected the rise of oxygen and the nutrient cycles that life depended on. Every cycle leaves a legacy. Every gathering changes the terms of the next world. Sometimes I think the supercontinent cycle is the Earth's slow way of refusing stagnation. Just when a world begins to feel settled, the deep forces start working against that settlement. Heat gathers below. Rifts appear. Oceans pry old unions apart. Fragmented lands wander. Then, when the wandering goes on long enough, the geometry of the globe and the logic of subduction begin to pull them back together. No arrangement lasts. That is the law. The map is temporary. The cycle is the constant. Even now, with our modern world feeling so definitive on the wall of a classroom, the motion continues. The Atlantic is widening as North America and Europe move apart. The Pacific, ringed by subduction zones, is slowly shrinking. Africa inches northward. Australia continues its determined slide toward Asia. California drifts on the Pacific plate with a kind of quiet geological mischief. Given enough time, and the Earth always has enough time, another supercontinent will form. Scientists have proposed names for these future unions: Pangea Proxima, Amasya, Novo Pangea, each depending on how the continuing motions are modeled. The exact arrangement remains uncertain. But uncertainty about the future map does not cancel certainty about the underlying rhythm. The land will gather again, which means the world we know is not an endpoint. It is merely between unions. Between breaths. That thought can be oddly soothing. It makes our usual sense of permanence feel lighter, less stern. The continents are still traveling. The oceans are still provisional. The mountains around us are not final. They are moments in a chain of moments. And perhaps that is why studying the older worlds feels less like antiquarian curiosity and more like listening closely to a living system. Rodinia, Nuna, Kenorland, These are not just names attached to dead maps. They are earlier notes in a melody still being played. The Earth has not finished its song. If you were to look at a modern map long enough, truly long enough, with the right kind of tiredness in your eyes and the right kind of patience in your breath, it might begin to feel animate. South America leaning toward old connections. Africa lifting north. Antarctica sitting in cold silence like someone keeping an old secret. India still pressed against Asia as if its long journey ended only yesterday. The continents begin to look less like objects and more like participants. Travelers, yes. Dancers, yes. But also witnesses. Each carries within it the sutures of old collisions and the fragments of older lands buried in its heart. Each has been somewhere else. Each has worn other neighbors. That is the world before that final famous supercontinent. Not a blank prelude. Not dead background. A full, long history of wandering lands and repeated unions, of hidden heat and returning geometry, of coastlines that could not stay loyal to themselves. And once you begin to feel the rhythm of that wandering, the next old face rises naturally out of the dark. Rodinia, the forgotten motherland, the giant ancient union that gathered the world long before animals walked the shore, then cracked apart and may have helped send the whole planet into ice. Rodinia arrives in the story like a lost kingdom, whose walls have fallen so completely that only the foundation stones remain. Even its shape is argued over. Scientists can tell that it existed. They can see the age of the rocks, the magnetic traces, the old scars where continents were welded together. But when they try to picture its full outline, the image wavers. One reconstruction turns North America into the central anchor. Another rotates the surrounding blocks into different positions. Australia, Siberia, parts of what would become South America and Africa. Old continental cores that now live far apart may once have leaned against one another in a silence so deep it almost feels ceremonial. That uncertainty is part of the mood. Rodinia is not a place we can know in the bright and easy way we know a modern map. It has to be approached like an old ruin at twilight, carefully, respectfully, aware that some of the walls are guesses and some are memory. Still, enough remains for us to walk there in the mind. Picture the Earth around 1 billion years ago. The planet is already ancient, beyond ordinary comfort. More than 3 billion years of volcanic labor, tectonic collisions, and oceanic change lie behind it. Yet the land, for all its age, would not have looked mature in the way modern landscapes do. There are no forests, no flowers, no birds crossing the evening sky, no insects making a soft electric hum above marsh grass, no grazing animals, no footprints gathering beside a river, no roots splitting rock in the patient way of pines and oaks. Land is not yet decorated by anything we would call familiar abundance. It is stone, heat, storm, and microbial persistence. Along the margins of Rodinia there would have been shallow seas, and in those seas life was already at work. Microbial mats spread across sediment in thin living films. Cyanobacteria continued their long, impossible labor, releasing oxygen bit by bit as a waste product, changing the chemistry of the atmosphere without ceremony. without applause, cell by cell. Stromatolites, those layered mineral structures built by microbial communities, rose in places like low stony gardens. They were not dramatic in the cinematic sense. No great animal moved among them. No fish flashed in schools overhead. But they mattered. They were among the quiet engineers of the planet. The land itself may have been harsh, especially in the interior. A supercontinent changes climate by sheer scale. Once, so much land is gathered into one broad body. The middle lies far from the ocean. Moisture struggles to travel inland. Temperature swings become stronger. Coasts still feel the moderating breath of the sea, but the heart of the continent can turn dry and severe. So the center of Rodinia may have stretched in long, barren distances, plains of rock and sediment beneath an atmosphere still not quite like our own. Wind moving over open ground. Dust lifting and settling. Rain falling rarely in some regions, more generously in others, but always onto a land almost empty of visible life. If you were standing there with me and somehow could breathe, I think the first thing you would notice would be the silence. Not the pleasant silence of snowfall or a late library, but a larger silence, one with almost no animal interruption. No hidden rustle in the brush because there is no brush. No flock lifting suddenly from the ground. No chorus after dark. Just the scrape of wind, the occasional crack of stone under heat and cold, the far sound of surf, where the margins meet the sea. Honestly, it would probably feel beautiful for about 3 minutes, and then unsettling for the rest of the night. Rodinia matters not just because it existed, but because of what happened after. Like every supercontinent, it did not remain whole forever. Heat built beneath it. The insulating effect of such a vast landmass may have helped trap mantle heat below. The crust weakened. Rifting began. Long fractures opened. Magma rose. New ocean basins started to form. Around 750 million years ago, give or take the usual geological arguments, Rodinia began to tear apart. This is one of the great turning points in the older story of the Earth. When a supercontinent breaks, the world changes in more ways than the map reveals. New coastlines appear. Ocean circulation alters. Weathering rates shift. Carbon dioxide can be drawn down or released depending on volcanic activity, erosion, and the placement of land relative to the equator. What looks like a tectonic event becomes a climate event, an ocean event, a biological event. And in the aftermath of Rodinia, the climate may have lurched into one of the strangest states Earth has ever known. The phrase Snowball Earth sounds almost playful at first hearing, which is unfair to the severity of it. It sounds like something one might toss at a friend on a winter afternoon. But the hypothesis itself is immense and eerie. During several intervals between roughly 720 and 635 million years ago, the planet may have become almost entirely frozen, or very nearly so. Ice reaching low latitudes, perhaps even the equator. Oceans sealed beneath broad, frozen surfaces. Continents sheathed in white. The whole world turned into a pale, hard sphere, reflecting sunlight back into space. There is debate. Of course. Some scientists favor a full global freeze. Others argue for a slushier version, belts of open water surviving in places, more breathing room for life. That caution matters. We cannot pretend certainty where the rocks still invite argument, but whatever the exact details, the evidence points toward extreme global glaciation, far beyond anything in recent geological memory. Imagine Rodinia already torn into drifting pieces, some of them sitting near the equator, where weathering can be especially effective at drawing carbon dioxide from the atmosphere. Imagine greenhouse gases falling. Imagine cooling that feeds on itself, because ice reflects light, and reflected light means less heat absorbed, and less heat absorbed means more ice. Once that machinery begins, the planet can slide into a self-reinforcing cold. Then imagine the silence of that world. No forests buried under snow, because forests do not yet exist. No mammals hiding in dens. No villages with smoke rising from roofs. Just ice on rock. Wind crossing frozen surfaces. Ocean water trapped beneath long white stillness. Life reduced to refuges, perhaps near volcanic regions, perhaps beneath thin ice, perhaps in protected marine pockets where light and chemistry still allowed survival. It is one of the reasons I find early Earth so haunting. Later disasters usually injure familiar life. A frozen Devonian coast, a dying reef, a forest gone to ash. We can feel those losses in borrowed detail, but these older crises happened in worlds already strange, already nearly empty of the familiar, and that makes them feel almost sacred in their remoteness. Life survived there not through drama, but through persistence, through smallness, through patience. Microbial life likely endured in those dark, cold intervals. And when the freeze finally loosened, the release may have been fierce. Volcanoes do not stop simply because the surface is frozen. They continue to release carbon dioxide. Over immense spans of time, that gas can build in the atmosphere, especially if weathering is reduced under ice. Eventually, greenhouse conditions strengthen enough to melt the frozen shell. A hard white planet gives way to rapid warming. Glaciers retreat. Water moves again. Nutrients flood into the seas. The climate swings from one extreme to another. I have always found it strange that some of the biggest turning points in the history of life sound, when reduced to textbook phrases, almost tidy, great oxidation event, Snowball Earth, breakup of Rodinia. The labels are so calm. They do not sound like a planet shuddering through states that would make any modern observer think the world had gone wrong. But the calmness of the label is only human shorthand. The actual events were immense. And after those freezes, something extraordinary began to unfold. Not instantly, not in the impatient way our century likes to imagine breakthroughs, but truly, in the late Ediacaran period, following those severe glacial intervals, the Earth saw the rise of larger and more complex multicellular organisms. The famous Ediacaran biota, soft-bodied forms, unlike much of what came later, spread in marine settings. Some looked like fronds pressed into sediment, some like quilted discs, some like delicate experiments that evolution would later set aside. They are not part of Rodinia proper in the strict timing sense, but they belong to the world Rodinia helped shape by forming, breaking, and perhaps nudging the climate into terrifying extremes. This is the great lesson of the old supercontinents. They are not scenery. They are causative. They change the terms of the game. Their assembly and breakup alter the oceans, the atmosphere, erosion, nutrient flow, and available habitat. They are active participants in the story of life. Rodinia may have done exactly that. By clustering the land, then fracturing it apart, it may have helped create the environmental instability that pushed the biosphere into a new chapter. A harsher world, yes, but also a more permissive one in the long run. More coastlines, more shallow seas, more nutrient input, more geochemical restlessness. It is tempting to think of stability as always good, but the history of Earth can be rude about that assumption. Sometimes stress opens possibilities. Sometimes destruction rearranges the stage in ways that allow new actors to appear. There is a humbling, almost comic side to it as well. We speak of continents as if they were dignified, and perhaps they are, but they are also troublemakers. They gather into giant dry unions, heat up from below, crack apart, fling climate into disorder, and then indirectly help make future complexity possible. It is not the polished behavior one expects from ancient crust. Very poor manners, in a geological sense. Still, Rodinia remains beautiful to imagine. Not beautiful because it was lush. It was not. Not beautiful because it was kind. It may have helped usher in brutal cold. Beautiful because it reveals how early the Earth had already begun performing these massive cycles of integration and dispersal. By the time later supercontinents formed, the planet was not trying something new. It was repeating an old habit. And Rodinia itself had ancestors. If we walk farther back, we leave behind even the sparse comfort of a late Proterozoic world and move into deeper time, into an Earth where the clues become dimmer and the names feel heavier. Before Rodinia came Nuna, sometimes called Columbia, depending on which geological tradition is doing the talking. It existed around 5 billion years ago, perhaps earlier in assembly, and it represents one of the earliest large-scale continental unions we can reconstruct with something like confidence. Confidence is still too strong a word for some details. That is one of the pleasures and frustrations of ancient geology. The older the world, the more every map has to be drawn with a pencil rather than ink. But enough ancient mountain belts, radiometric ages, and paleomagnetic records align to suggest that North America, Greenland, Baltica, Siberia, India, Australia, and parts of South America were once connected in a broad supercontinental arrangement. Nuna does not arrive to us with the dramatic climate mythology that follows Rodinia. It is older, quiete in our reconstructions, less flashy to modern imagination. Yet there is something almost more haunting in that quiet. A giant landmass in a world without trees, without animals, without any obvious witness except microbes and stone. A world under a weaker sun, with an atmosphere still evolving, with long, stable spans that scientists once jokingly called the boring billion. I never trust a phrase like that. The boring billion. It says more about human impatience than about the planet. Because from the point of view of the Earth, and perhaps from the point of view of a careful listener. There is nothing boring about an interval in which continents gather. Oxygen slowly accumulates. Oceans change chemistry, and the preconditions for future complexity are being laid grain by grain and molecule by molecule. Still, I will let Nuna wait for us a little longer, just at the edge of the firelight, because before we step fully into that older world, I want the image of Rodinia to finish settling in your mind. A motherland of rock and shallow seas, a giant union assumed from ancient Kraton, an interior of likely dryness and silence. A breakup that fractured the world and may have nudged it toward global ice. A vanished face of Earth that no human ever saw, yet one whose consequences still live beneath our continents and inside the very possibility of our existence. And when Rodinia finally loosens its hold, another older giant rises behind it, broader in age, dimmer in outline, waiting in the deeper dark. Nuna, the earlier union, the older ancestor, the land that gathered before even Rodinia knew how to break. Nuna asks for a slower voice. Rodinia, at least, still feels close enough to the edge of complexity that the imagination can find handholds. There are the glaciations, the later Ediacaran world, the first large multicellular experiments waiting beyond the cold. But Nuna lies farther back, around 8 billion years ago, in a world that can feel almost too stripped down for narrative unless you learn to love the quiet details. And I do. I think maybe that is why this period lingers with me. It is a nearly empty stage, but the stage itself is being built with such seriousness that you begin to understand how much of history depends on preparation. Nuna, also called Columbia by some geologists, was one of the earliest clear supercontinents, a giant union of ancient cratons that would later become the hearts of modern lands. North America, Greenland, Baltica, Siberia, India, Australia, maybe parts of South America. Old continental cores that are now oceans apart may once have been assembled into one long enduring mass. The exact arrangement remains debated, and that is worth saying gently and often. Deep time does not always reward arrogance. The farther back we go, the more humility becomes part of the method. Still, the evidence is persuasive. Matching ancient mountain belts, similar ages of crust forming and colliding, paleomagnetic clues preserved in minerals that cooled and locked in a record of latitude. When all those fragments are compared, Nuna appears, not as a crisp photograph, but as a shape emerging through fog. The world of Nuna had no forests to soften the land, no grasses, no flowers, no animals on shore. If you walked there, again setting aside the problem of breathing and survival, you would find expanses of bare rock, weathered surfaces, volcanic highlands in places, river systems crossing ground with little rooted life to hold it together. Along the margins there would have been shallow seas, and those seas were the true living skin of the planet. Microbes, cyanobacteria, stromatolite building communities, simple eukaryotic life, all continuing their ancient labor. It is during the time around Nuna that people sometimes place part of what used to be nicknamed the boring billion, a long interval when life did not appear to leap dramatically in the fossil record. I understand why the nickname stuck. Human beings adore obvious breakthroughs. We notice fireworks, not patient architecture. But this interval was not empty of importance. It was full of preparation. Oxygen levels were changing. Nutrient cycles were shifting. Stable continental shelves offered long-lived, shallow marine environments where microbial ecosystems could thrive and diversify. The chemistry of the oceans and atmosphere was moving, even if slowly, toward futures not yet imaginable. There is a kind of stern beauty in a world that is not yet ready for spectacle. If Rodinia feels like a dark hall before dawn, Nuna feels like the long breath before a sentence. Extended, controlled, foundational. Its assembly involved massive collisional events, ancient cratons drifting together, mountain belts rising where oceans closed between them, crust thickening, metamorphic rocks forming deep below. The roots of those mountain chains survive in places like Canada and Greenland, in old shields where the surface has been eroded down so far that what remains is not the mountain itself, but the deep compressed bones beneath it. The word shield is a good one. These rocks feel defensive, ancient, difficult to erase. They are among the surviving memories of a world almost no other evidence still describes. What would the climate of Nuna have been like? Warmer in some respects than the modern world, perhaps, though still variable and not beyond episodes of cooling. The sun itself was fainter than it is now, which is one of the great early paradoxes. A dimmer sun should have left Earth frozen, and yet liquid water persisted for most of its history. Greenhouse gases, methane earlier, carbon dioxide, and the complex feedbacks of atmosphere and ocean chemistry helped compensate. By Nuna's time, oxygen had risen from truly negligible beginnings, though not to modern levels. The sky may have looked more familiar in some intervals than in the deepest Archean, but still not wholly ours. I sometimes picture the color of that sky and then stop myself, because it is so easy to let imagination outrun evidence. Better to say this: the atmosphere was different enough that a modern observer would likely feel the difference immediately. The air pressure, gas mix, and chemistry were not those of a human world. The oceans beneath that sky held much of the interesting biology. Land was still mostly a geological statement. And yet geology is never only geology on Earth. Collisions build mountains. Mountains erode. Erosion delivers nutrients to rivers and then to the sea. Nutrients feed microbial productivity. Productivity changes oxygen and carbon cycles. Those cycles shape climate. Climate shapes habitability. The chain never really breaks. The old supercontinents show again and again that the boundaries between stone, sea, and life are softer than they first appear. Nuna may have been especially important in that sense. Large, stable continental platforms mean long, broad margins. Margins mean shallow seas. Shallow seas are fertile and chemically influential. Even a world dominated by microscopic life can be deeply transformed by the shape and arrangement of its land. If you stand in imagination on a Nuna shoreline, the scene is austere, but not dead. Shallow water stretches outward under a patient sky. Thin microbial films darken wet surfaces. Stromatolites rise like low, stony domes. Their layered forms, built by lives too small to see individually. Waves slide in and out across a coast with no shells, no driftwood, no bird tracks. The smell would not be the smell of a modern beach. No rotting kelp, no salt mixed with flowering dune grass. More mineral, more iron perhaps, more wet stone, less sweetness, less decay in the familiar sense. Its breakup began eventually, because all supercontinents break. Heat beneath a broad continental lid builds. Rifting begins. The crust thins and opens. New ocean basins form. Pieces drift away. Nuna did not shatter theatrically in the way our minds might prefer, but slowly, over tens and hundreds of millions of years, its unity loosened. The fragments that would later contribute to Rodinia wandered into new relations. The Earth rearranged its furniture again. By the time Nuna yields to other configurations, we are already close to another older threshold, Kenorland. Now there is a name that feels as if it ought to be spoken near coals, not fluorescent office lights. Kenorland belongs to a much earlier Earth, around 7 billion years ago, in the late Archean to early Proterozoic transition, depending on which portion of its history we mean. The evidence for it is older, is scarcer, and more argued over than for Rodinia or Nuna. But many geologists see in the oldest cratons and mountain building events the signs of another early supercontinental assembly, pieces that would become parts of North America, Scandinavia, Southern Africa, and Western Australia may once have been joined in one of the first large continental unions. Kenorland is where the story starts to feel truly alien. The sun was dimmer still. The atmosphere carried far less oxygen. Cyanobacteria were at work, yes, but the world they were changing had not yet yielded easily. Methane and carbon dioxide played large roles. The land was barren in a more total way, not merely lacking forests, lacking anything like visible terrestrial ecology. Rock, sediment, water, volcanic activity, microbial life mostly confined to marine and wet environments. A world that, to modern senses, might feel like a strange half-finished draft of Earth. And yet, during or after the time of Kenorland, the planet experienced one of its greatest chemical transformations, the Great Oxidation Event. Again, the phrase sounds so tidy. Great Oxidation Event. It could be the title of a lecture attended by polite people with notebooks. In reality, it was one of the most consequential revolutions the Earth has ever undergone. For hundreds of millions of years, oxygen produced by photosynthetic microbes had been quickly consumed by reduced minerals and dissolved iron. But eventually those sinks began to saturate. Oxygen started to accumulate more persistently in the atmosphere. The effects were astonishing. Iron in the oceans reacted with oxygen and precipitated out, forming banded iron formations, red and black layered rocks that we still mine today. Methane, a strong greenhouse gas, was reduced, which may have contributed to severe global cooling. Some of the earliest major glaciations, the Huronian glaciations, may be tied in part to this atmospheric transformation. A warmer methane-rich world gave way to a colder one. For anaerobic life, oxygen was not a gift. It was a poison. Entire microbial communities likely retreated to protected niches or vanished. For the future of complex life, though, oxygen opened doors that would remain closed in an anoxic world. Imagine standing on a shore from that age. The air is not breathable to you. The sky may carry a tint unfamiliar to modern life, depending on the exact interval and atmospheric mix. The ocean stretches out, not empty, but alive with microbial worlds invisible at a glance. In shallow waters, mats spread like dark, living carpets. Inland, the land is silent, beyond any modern silence. Wind over rock. Occasional volcanic rumblings in the far distance. No grass bending. No tree line. No animal cry. And yet, beneath that quiet, the world is being rewritten. Tiny organisms are altering the atmosphere of the whole planet. That fact never really loses its power. The biggest revolutions in Earth's history are sometimes made by the smallest workers. Kenorland did not last. None of them do. Rifting, dispersal, new ocean basins, drifting fragments. The cycle continued. And with every cycle, the crust itself thickened in places, stabilized in others, building the old continental cores, the cratons, that remain as the deepest anchors of modern continents. The Canadian Shield, the Kapval Craton, the Pilbara Craton, the hard old hearts of the world. And then, farther still, there is may not have been a supercontinent in the grand later sense. It was smaller, older, more like a seed than a giant. Formed perhaps around 3 billion years ago, maybe a little earlier depending on how one defines it. Is sometimes treated as one of the earliest recognizable continental masses whose fragments may still survive inside younger continents. South Africa, Western Australia, parts of India, perhaps Madagascar. Old Archean crust that may once have belonged to a coherent early landmass. Feels like the beginning of land that stayed, not the first crust ever formed. Likely not. Earlier protocontinents may have existed and been recycled into the mantle. But may represent one of the first enduring pieces. Crust thick and buoyant enough to survive and become the nucleus for future growth. The Earth in time was hotter. The mantle more vigorous. The crust thinner and more vulnerable. Oceans likely covered most of the world. Stable continental land was scarce. For a piece of crust to persist under those conditions was extraordinary. May have been small compared with later continents, perhaps only a fraction of the size of modern Africa. But persistence matters more than size in this part of the story. A small continent that survives can become the foundation for everything that follows. There is a tenderness to that. The first durable land was not grand. It did not dominate the globe. It simply endured. Later collisions added to it. Later supercontinents incorporated its fragments. It became part of larger wholes without losing its deepest identity. A modest beginning with an immense afterlife. The rocks that may belong to are among the oldest preserved on Earth. They are not easy storytellers. They have been heated, deformed, buried, exhumed, cut by later intrusions, and weathered across almost unimaginable spans. Reading them is less like reading a book and more like listening through static for a voice that refuses to disappear. Isotopes, mineral ages, structural relationships, faint magnetic signals. From those whispers, geologists infer an old small continent that may have become one of the first stable seeds of the later world. What did look like? Spare, harsh, volcanic in places, coastlines uncertain, shallow marine shelves hosting microbial life, land mostly barren, atmosphere low in oxygen, the sky under a younger, dimmer sun. A planet more dangerous and less forgiving than the one we know, but already building the conditions from which a gentler surface would eventually emerge. If Rodinia was the motherland and Nuna the older ancestor, was the first stubborn child who survived. That brings us to one of the deepest truths of all this wandering. Continents do not merely move, they grow. Early Earth likely had smaller, more fragile land masses. Through volcanic arcs, collisions, accretion, and survival, those fragments thickened, merged, and became more stable. The continents of today are mosaics, patchworks, layer upon layer of old worlds welded together. A modern landmass is not one thing. It is an archive of unions and breakups, of borrowed terranes, sutured margins, and ancient cores. The ground beneath your feet may include pieces that once stood in were folded into Kenorland, carried through Nuna, packed into Rodinia, and then inherited again by later worlds. There is almost no polite way to respond to that except awe. Still, awe is the stronger response. The worlds before the later famous supercontinent were not empty preludes. They were real, distinct, harsh, foundational. Kenorland, Nuna, Rodinia, seeds, union, breakups, recoveries, worlds of rock and microbial labor, worlds where climate, chemistry, and crust were preparing the stage long before forests learned to cast shadows. As the fire settles and the room grows a little softer around us, let this older chain of worlds rest in your mind as one long preparation. Tiny, enduring land, early giant union, oxygen rising, ice coming, continents gathering and breaking in the dark, the earth teaching itself how to be a home. And from these hardest, oldest worlds, from these barren continents and patient seas, another theme begins to rise. Not just land, but water. Not just the continents themselves, but the vanished oceans that opened between them, ruled them, closed again, and carried the first great empires of life in their depths. If the continents were the bones of the ancient earth, then the oceans were its long breathing skin. Before forests, before reptiles, before anything with a face could lift itself toward a horizon and wonder what waited beyond it, water ruled almost everything. Land wandered. Land collided. Land broke apart. But the seas held the planet together, not in the sense of permanence, because oceans also came and went, but in the sense of presence. There was always water somewhere. There was always a basin receiving rivers, cradling chemistry, carrying heat, and giving life a place to try again. It is easy for us to imagine oceans as fixed because we memorize their names early and keep them like household objects. Pacific, Atlantic, Indian, Arctic. But those names belong only to the current arrangement. Before this map, there were other oceans, older ones, wider ones, stranger ones, each tied to a different arrangement of drifting continents. Some lasted for hundreds of millions of years, long enough for whole ecosystems to rise and vanish within them. Then they closed, crushed between approaching lands, their floors dragged into the mantle, their sediments lifted into mountain ranges. Their water did not disappear, but the ocean itself as a place, as a basin with a history and a shoreline, died. That is one of the quiet heartbreaks of geology. Even oceans are temporary. One of the great old seas was the Iapetus Ocean, opening roughly 600 million years ago between Laurentia, Baltica, and other drifting continental fragments. It spread wide and carried early marine life across a world still rearranging itself after the older supercontinents. Along its floors, trilobites moved over sediment. Brachiopods filtered water through their shells. Early fish and strange soft-bodied creatures lived in its shallows and shelves. It was not merely water between land masses. It was an active world, full of current, chemistry, and life, a stage on which evolutionary experiments unfolded. Then the plates kept moving. Subduction consumed the floor of the Iapetus. Continents drifted closer. Island arcs collided. The basin narrowed. Eventually the ocean closed, and the scars of that closure remain in the mountains of eastern North America, Scotland, Scandinavia, and parts of Greenland. The Appalachians and the Caledonian Ranges are not just mountains. They are the folded memory of a vanished sea. When you stand in those mountains today, you are standing where an ocean once lived, where sediments settled quietly on a sea floor that no longer exists. I have always loved that fact because it feels almost impolite. Mountains, pretending to be permanent, while deep inside them sits the confession that they began as ocean. Before the Iapetus, there were older waters. Mirovia may have surrounded Rodinia, a global ocean around a supercontinent that itself no longer stands. Later, Panthalassa stretched around Pangea, a vast world ocean covering most of the globe, so large that it makes the modern Pacific feel almost like a surviving fragment of an older empire. Then there was the Tethys Ocean, that elegant shifting seaway between Gondwana and Laurasia, whose closure would later help form regions around the Mediterranean and the high folded belts of Eurasia. The names sound almost mythic, and perhaps that is fitting. These oceans have become more like remembered kingdoms than places. Yet they were physical, measurable, real. They opened when continents rifted. They widened when new seafloor formed at ridges. They narrowed when subduction pulled that seafloor downward again. Their births and deaths were written into basalt, sediment, fossils, and mountain belts. If you could stand on one of their shores, and I know we keep performing this impossible little trick of survival and observation, but it helps. What would feel familiar? Waves. Always waves. The rhythm would still be recognizably oceanic. The scent might be less familiar, depending on the time and biology involved. In a world before land plants, a shore would not carry the sweetness of vegetation or the soft rot of coastal woods. In a microbial world, it would smell more mineral, more marine, more like wet stone and chemistry. The horizon would still divide sea and sky in the same patient way, though the color of the sky might shift with the atmosphere of the age. And the beach itself might be almost shockingly bare. No bird tracks, no crab holes, no dune grass, no driftwood tossed up after a storm. Just sediment, salt, rock, and water working at one another. The oceans shaped climate as much as land did. Currents transport heat. Salinity affects sinking and rising waters. Coastlines determine circulation paths. A supercontinent changes the movement of water simply by existing. Gather land into one broad body, and circulation must adapt. Break it apart, and new routes open. The position of continents relative to the poles and equator alters where warm water can flow and where cold water can sink. The climate of any ancient world cannot be understood without its seas. Water carried the temperature of the planet around like a slow, invisible messenger. The oceans also controlled chemistry in ways that feel almost parental. They buffered the atmosphere. They absorbed and released carbon dioxide. They hosted the first widespread life. They stored dissolved minerals. They recorded volcanic outpourings, weathering pulses, oxygen crises, and recoveries in their sediments. If the continents were always wandering and the volcanoes always shouting, the oceans were the immense, patient record keepers. And yet, they were not gentle. Sea levels rose and fell repeatedly. When ice expanded on land, shallow marine habitats shrank. When the climate warmed and water returned to the sea, coastlines drowned and inland seas spread across continents. There were times when broad, shallow epicontinental seas covered huge portions of land masses, turning what we now think of as stable continental interiors into warm marine environments filled with life. North America, during parts of the Paleozoic, spent long intervals beneath shallow water. Imagine that. Entire familiar regions under sunlit sea, with no cities, no mammals, no human names, only brachiopods, crinoids, trilobites, and fish moving through clear ancient water above what would one day become fields and roads. Even more striking is the fact that ocean closure is not only a geological event, but an ecological one. When a basin narrows, marine corridors vanish. Populations are cut off or forced into new competition. Reefs may be lost. Nutrient cycles shift. Shallow shelf environments disappear. The closing of oceans has repeatedly reshaped life, sometimes gradually, sometimes with enough force to become part of larger extinction patterns. That brings us to the sky above those seas, because ocean and atmosphere have always been partners in the oldest story. The atmosphere of ancient Earth was not simply an earlier version of modern air. It was often profoundly different. The earliest atmospheres were likely rich in gases released by volcanic outgassing. Water vapor, carbon dioxide, nitrogen, methane, ammonia, little to no free oxygen. A world under such a sky would not feel like ours. The color may have been altered by haze. the chemistry would have been hostile to modern lungs. Ultraviolet light from the sun would have reached the surface more harshly before an ozone layer developed. This is one of those places where the imagination has to move carefully. We cannot paint every sky with certainty. But we know enough to say that Earth has worn atmospheres so different that a modern human would not recognize the air as home. In the Archean, before oxygen accumulated significantly, methane may have played a major role in keeping the planet warm, despite the fainter young sun. That idea still amazes me. The sun was weaker, and yet the Earth remained wet because greenhouse gases did the heavy lifting. A haze-rich atmosphere under a dimmer star, oceans below, scarce, stable land, microbes already at work. It sounds almost like another planet. And in a way it was. Not another world in space, but another version of this one. Then came the long, patient labor of cyanobacteria and other photosynthetic microbes. They split water. They used sunlight. They released oxygen. At first, that oxygen was quickly consumed by reduced materials, especially iron in the oceans. Vast, banded iron formations formed as iron reacted and settled out in layers. Red and black, black and red, ancient rust, written into stone. Only after those sinks became saturated did oxygen begin to persist more substantially in the atmosphere. The Great Oxidation event was not a single afternoon. No matter how much the phrase makes it sound like someone opened a window, it unfolded over immense spans. But its consequences were severe. Methane levels fell. Climate may have cooled dramatically. Anaerobic organisms faced a crisis. Oxygen, which later life would treat as a gift, arrived at first as a toxin to many older forms. I sometimes think of it as one of the darkest jokes in biology. Tiny life works for ages to change the world, and in doing so poisons part of the world that came before it. Still, oxygen allowed new possibilities. More energetic metabolisms. Eventually, ozone. Eventually, protection from harsh ultraviolet radiation. Eventually, the conditions that would permit complex life to flourish near the surface and later on land. The sky became not just a lid over the world, but a partner in habitability. Oceans and atmosphere kept changing together. Carbon dioxide rose during intervals of heavy volcanism. Weathering drew it down. The burial of organic carbon altered balances. Sulfur cycled through air and water. Anoxic oceans spread during some intervals, depriving marine life of oxygen in deeper waters. At other times, better oxygenation and circulation transformed what could live where. Ancient climates moved between greenhouse warmth and severe glaciation, not because one system changed in isolation, but because all the great systems of Earth were linked. If you were listening closely enough to the planet, the seas and the sky would sound like two halves of the same long sentence. There is also the question of color, and here I allow myself a little softness, because while evidence guides us, imagination completes the room. Under methane haze, the sky may have leaned toward orange or dull gold. Under later, more oxygen-rich conditions, it would have turned bluer, more like the one above us now. But even a familiar blue over an unfamiliar shore would feel uncanny. You know that feeling when you visit a place that has all the right pieces? Sky, wind, shoreline, but the proportions are slightly wrong. and suddenly your body understands that you are not where you thought you were. Ancient Earth would have done that constantly. A recognizably earthly sea under an unrecognizably ancient atmosphere. And yet, through all these strange arrangements, life persisted in the water. The oceans were not static tanks waiting for better times. They were inventive. They hosted the first eukaryotes. They nurtured multicellular experiments. They absorbed the consequences of volcanic gases and delivered nutrients from eroding land. They froze under global ice and still protected life below. They carried the memory of every continent that broke apart and every atmosphere that changed. By the time later complex life begins to step toward the shore, the oceans have already done billions of years of preparatory work. They have built chemistry, moderated climate, hosted innovation, and tolerated catastrophe with a patience that borders on holy. So when we leave them for a while, when we turn from ancient seas and ancient skies toward the first hesitant life on land, we should do it with respect. The shore was not where life began. It was where life graduated into a harsher classroom. And the first students were not dramatic heroes. No fish with immediate swagger. No instant forests. The beginning on land was smaller, softer, and much braver than that. A film on stone. A mat at the margin. A few green pioneers leaning into a world that had been empty for almost the entire history of the planet. There were times when seawater itself carried the signatures of catastrophe. Ash from eruptions. Carbon shifts from dying ecosystems. Layers of mud laid down in anoxic depths where almost nothing stirred. Then above those same dark records, later life would return, as if the ocean were forever practicing the art of recovery. That may be the most oceanic lesson of all. Nothing remains arranged forever, and yet life keeps using every new coast and every new basin as another chance to begin. So let the sea withdraw now, just enough for us to follow those first green and many-legged pioneers farther inland. The shoreline has done its work. The continents are no longer only stone. They are about to become inhabited in a way that even the old oceans could not have predicted. For billions of years, the continents were mostly scenery. Immense scenery. Yes. Moving. Colliding. Splitting. Rising into mountains and sinking under shallow seas, but still largely empty of visible life. Water had the creatures. Water had the experiments. Water had the first true complexity. The land waited under strange skies and let rain carve it into shape. Then, very slowly, life began to move toward the shore. Not with a grand march. Not with a beast hauling itself heroically from the surf while trumpets blared somewhere in the evolutionary distance. The first colonization of land was quieter than that, which is probably more honest and certainly more beautiful. It began with microbes, thin living films spreading across damp surfaces, clinging to rock where water lingered, surviving at the edges of pools and shorelines. The early land was severe, drying, ultraviolet, radiation, temperature swings, bare mineral ground, all of it stacked against soft life. But tiny organisms are stubborn in ways that never make headlines. Microbial mats likely crept over wet rock long before anything like a forest existed. They stabilized sediment. They trapped moisture. They turned raw surface into a more habitable skin. This matters more than it first appears. Before roots and leaves and soil, there had to be something to begin softening the interface between stone and life. Microbes did that work. Then, later, came plants, if we are generous with the word at first. Small moss-like organisms, liverwort-like pioneers, low to the ground, simple, lacking the woody confidence of later forests. Around 470 million years ago, perhaps a little earlier in tentative forms, land plants began to appear in the record. They were not tall. They were not elegant in the modern sense. They stayed close to moisture, reproduced by spores, and spread across damp environments in thin green patches. But their arrival was one of the most revolutionary events in Earth history. A bare continent and a continent with even a little plant life are not the same world. Once, plants began to hold the ground. Soils developed more fully. Weathering intensified. Carbon dioxide was drawn from the atmosphere. Organic material accumulated. Water moved differently across landscapes. Instead of rushing unchecked over raw rock, it began to seep, pool, and interact with growing layers of life and sediment. The green fringe at the edge of the old world widened. I have always found it moving that the first land plants were so modest. The great transformation began not with majesty, but with little green persistence hugging wet ground. It feels like the planet was whispering before it learned to sing. By the Silurian and Devonian periods, plants had become more ambitious. Vascular systems evolved, allowing water and nutrients to move internally through stems and tissues. That changed everything. A plant no longer had to remain a tiny, damp, skimming thing pressed to the ground. It could rise. It could grow upward and outward. It could risk dry air more boldly. Cooksonia and other early vascular plants look almost simple to the point of comedy when compared with later trees. Little branching stalks with capsules at their tips, but in their own time, they were astonishing inventions. And then forests arrived. The first true forests transformed not only the appearance of the land, but the chemistry of the planet. By the late Devonian, trees like Archaeopteris had woody trunks, to branch, leaves, and root systems capable of reworking the landscape. Imagine that transition. A world where for most of its history a horizon met mostly bare ground and low green mats. And then, in geological terms rather suddenly, vertical life appears. Shade appears. Leaf litter appears. Root webs bind soils. Rivers change their behavior because the ground is no longer loose and naked. The air changes because photosynthesis now happens on a scale the old world never knew. The first forests were not made of oaks or pines. They were strange, lycopsids with tall, scaly trunks, giant horsetails, fern-like growths, seed ferns, trees with forms that would look almost theatrical to modern eyes. Some rose 30 meters or more, towering over wet landscapes. The forest floor would have been thick with damp growth, fungal threads, decaying organic matter, and the first truly complex land, food webs. This changed the atmosphere. As plants spread and buried carbon in soils and later coal deposits, carbon dioxide levels fell. Oxygen rose. During parts of the Carboniferous, oxygen may have reached levels significantly higher than today. And that rich air did something memorable. It made giants possible. Arthropods had already been on land for some time. Millipede-like animals, early scorpions, insects, and other hard-bodied pioneers found ways to use the new green world. But under high oxygen, some of them became enormous. Arthroplera, that great many-legged animal, stretched longer than a person. Dragonfly relatives with wide wings moved through the forest air. Giant scorpions and centipede-like creatures occupied shadowed undergrowth and wet ground. It is one of those parts of prehistory that sounds as if someone is making it up to impress a child. But the rocks insist. If you were standing in one of those Carboniferous forests, the air would feel heavy and rich, the ground wet underfoot, the trunks tall and strange, the smell thick with decay and plant sap. No birds, yet singing overhead. Instead, the hum and rustle of enormous insects, the ripple of leaves in humid air, the distant movement of amphibians through blackwater pools. It would feel alive in a new way, a land no longer waiting but occupied. And amphibians did come, of course. Before reptiles ruled anything, before eggs with hard enough shells freed vertebrates from constant dependence on water, there were the lobe-finned fish and their descendants, edging toward a life between worlds. Some fish had already evolved lungs or lung-like structures to survive in oxygen-poor waters. Some had robust fins that could brace against mud and shallow bottoms. Tiktaalik is famous because it preserves that beautiful in-between quality. Fish and almost something more, but it was one member of a broader transition. By the late Devonian and into the Carboniferous, early tetrapods and amphibians entered the story. They were tied to water in crucial ways. Their eggs required moisture. Their young often remained aquatic. Their skin was not built for long dry exposure. But in swamps and wet forests they flourished. Some grew large, crocodile-like in body, broad-headed, patient hunters along the edges of pools and channels. Others stayed smaller, feeding on insects and other invertebrates. The move onto land was not a clean departure from the sea. It was a long, awkward negotiation. And then came one of the most consequential inventions in the history of vertebrates, the amniotic egg. Once early reptiles evolved, eggs protected well enough to survive away from open water. A vast door opened. No longer bound to ponds and swamps for reproduction, vertebrates could move more freely into drier environments. That is why reptiles matter so much in the prelude to Pangea. They turned land into a deeper possibility. The earliest reptiles were small, quick, and perhaps not particularly glamorous by later standards, but they were liberating their lineage from old limits. Over time, those lineages would split and diversify into forms that would lead toward mammals on one branch and toward dinosaurs, birds, and many other reptiles on another. But at the beginning, they were simply practical creatures in a changing world, slipping between roots and across drier ground, while amphibians still held the wetter realms. All of this unfolded while the oceans remained full of their own astonishing life. The seas of the Paleozoic were not background decoration. They were crowded, dangerous, inventive. Trilobites still marked many seafloors in earlier intervals. Brachiopods spread in abundance. Crinoids lifted feathery arms into currents. Corals and stromatoporoids built reefs. Straight-shelled cephalopods moved through ancient water like pale living spears. Then came the fishes. The Devonian is called the Age of Fishes for good reason. Jawless fish had appeared earlier, but the Devonian saw a flowering of jawed forms, armored placoderms, early sharks, ray-finned fish, lobe-finned fish, and lineages whose descendants still live in one form or another. Dunkleosteos, that heavily armored predator, moved through Devonian seas with a head like a dark machine made of bone. Not because evolution intended to be theatrical, but because predation has always loved innovation. Reefs expanded, then collapsed in later crises. Marine ecosystems became layered and complex. Predators hunted. Prey armored themselves. Filter feeders thickened communities across shelves and slopes. Ancient oceans had their own empires, and they rose and fell just as surely as forests did on land. There is an important emotional truth here. When we say ancient Earth was alien, we do not mean lifeless. We mean filled with life, arranged in unfamiliar ways. A shoreline in the Devonian or Carboniferous would not be empty. It would be thick with smell, humidity, spores, insect wings, amphibian skin, giant roots, and nearby water carrying fish and invertebrates beneath the surface. A different Earth, but not a silent one anymore. Climate, meanwhile, kept shifting with all of this. The first forests drew down carbon dioxide and likely helped cool the planet. Late Paleozoic glaciations spread across Gondwana. Ice sheets expanded in the southern hemisphere, while equatorial regions still held swamp forests that would later become coal. This combination feels almost unfairly dramatic. Glaciers in one great part of the world, steaming green wetlands in another. That is what continental arrangement can do. That is what atmospheric change can do. The Earth is not a creature of one mood. Mass extinctions struck too. The late Devonian crises damaged reefs and many marine groups. Environmental shifts, possible ocean anoxia, climate stress, and maybe other factors combined to prune the living world. Again and again the pattern repeats. Flourishing, stress, collapse, renewal. The forests changed the air. The air changed animal size and metabolism. The continents changed rainfall and seasonality. The oceans reflected the chemistry of all of it. No single realm was ever separate for long. By the time the later Carboniferous moved toward the Permian, the continents were converging toward a grand reunion. Swampy forests covered broad equatorial belts. Amphibians and reptiles spread through them and beyond them. Giant insects still haunted the air, though that age would not last forever. As oxygen levels shifted and climates changed, many arthropod giants would diminish. Reptiles would continue their rise. The long tectonic road to Pangea was nearly complete. And here, I think, is where the older world starts to feel unexpectedly close to us. Not because its creatures looked familiar. Many did not. Not because its forests resembled ours. They did not. But because by now the planet had acquired the structure of an inhabited Earth. Land ecosystems had layers. Predators and prey moved through shade. Rivers wound through rooted landscapes. Air and climate responded to life at scale. The continents did not simply exist. They hosted worlds. If you stood at the edge of a carboniferous wetland at dusk, the light would fall through strange tree forms and broad spore-bearing crowns. Pools would hold still dark water. Amphibians would shift just beneath the surface. Enormous insects might pass overhead with a dry, rattling wing beat. The smell would be thick with mud, rot, and living green. And somewhere beneath your feet, under the roots and O's, future coal would wait in silence, storing sunlight for creatures not yet evolved. That is the kind of thought ancient Earth keeps giving us. Nothing is merely present. Everything is becoming something else. Forests become atmosphere change. Swamps become coal. Fins become limbs. Wet, low plants become towering woods. Wandering continents become a supercontinent. So when we move on from here, when we follow the final approach toward the assembly of Pangea and the world it made, we do not leave behind a simple planet. We leave behind a planet already dense with consequence. Forests have changed the air. Oceans have changed the body plans of life. Land animals have begun their great branching. The old empty continents are empty no longer. They are crowded now, green in places, icy in others, humid along equatorial belts, restless beneath with tectonic force, full of giant insects, amphibians, and early reptiles, all living under skies that the biosphere itself has altered. And the land masses keep drifting, always drifting, drawing together, almost touching, preparing one more time to become a single enormous body, one more face for the Earth to wear before it changes again. And now the continents, after all that wandering, all that drifting through vanished seas and under skies that kept rewriting themselves, begin to lean toward one another with a new seriousness. The world is not finished changing. It never is. But there are ages when the motion feels less like a scatter and more like a gathering. This was one of them. To understand what it means for continents to collide, you have to set aside the human sense of impact. We hear the word collision and imagine sudden force, a crash, an ending. The Earth does not work that way. Its greatest impacts can take tens of millions of years. A shoreline does not wake one morning to find a mountain range where an ocean once stood. Instead, the sea narrows, bit by bit. Volcanic arcs appear. Earthquakes mutter through the crust. Sediments pile in deepening basins. Islands are sutured to continents. Pressure accumulates. Then, after spans of time so large they resist ordinary thought, the ocean is gone, and stone is folded into stone. That is how the road to Pangea truly began. Not as a single destination, but as the latest expression of an old planetary rhythm. After the breakup of Rodinia, the world spent long intervals as a patchwork of land masses and oceans. Laurentia drifted. Baltica wandered. Avalonia moved like a smaller, restless fragment with a future larger than its size might suggest. Gondwana, immense and heavy in the south, carried within it the ancient pieces that would become South America, Africa, Antarctica, Australia, and India. These were not yet the familiar countries and continents that later maps would pretend were inevitable. They were tectonic actors still finding their positions. The oceans between them were not empty space. They were active, narrowing or widening depending on the hidden logic of plate motion. Among them, the Iapetus began to close. Subduction consumed its floor. Island arcs were dragged inward. Sediments were scraped and folded. Continental edges were armed with volcanoes and deep trenches. Then came the collisions. Laurentia, Baltica, and Avalonia drew together first in important stages, closing parts of the old sea between them. This gave rise to mountain-building events whose remnants still survive in the Appalachians and the Caledonian ranges of Europe. Those mountains were once far higher than the softened versions we know now. Fresh, sharp, newly raised belts of stone, born from the slow crushing together of once separate lands. It is strange to think that a modern hiker in Scotland or the eastern United States is walking through the worn roots of collisions so old that the oceans involved have vanished almost beyond imagination. I have always found mountain belts a little theatrical. They are what the earth does when it wants to leave a record in raised handwriting. But the script kept going. Gondwana moved northward. Oceans narrowed further. The Reich Ocean, another of those vanished waters whose name now feels more like an echo than a place, slowly disappeared as Gondwana approached Euramerica. The combined landmass formed from Laurentia, Baltica, and Avalonia. Their convergence reshaped coastlines, reorganized shallow seas, altered climate belts, and raised yet more mountains. The continents were not merely meeting, they were knitting together. By the late Carboniferous and into the Permian, the union became unmistakable. Pangea emerged, a vast supercontinent stretching nearly from pole to pole, wrapped by the enormous global ocean Panthalassa, with the Tethys lying to the east like a lingering interior breath of sea between major landmasses. If earlier supercontinents had been difficult to picture, Pangea carries a special clarity because its descendants are the continents we know. South America pressed against Africa. North America fit against Europe and northwestern Africa. India remained attached to Gondwana, still far from the collision that would someday raise the Himalayas. Antarctica and Australia sat deep in the southern reaches of the world. And with this arrangement came a new planetary mood. Supercontinents do not merely change maps. They change weather, water, seasonality, and the emotional geometry of the land itself. The interior of Pangea was immense, far from the moderating influence of the sea. This meant deep dryness in many places, severe seasonal contrasts, and deserts spread across broad central regions. Along the coasts and in equatorial belts, conditions could still remain humid, especially in earlier intervals when lush coal swamps flourished. But the assembled landmass created environmental contrasts on a scale modern Earth only hints at. If you were standing in the middle of Pangea, far from any ocean, you would be in a world different from the maritime continents of today. The air would carry the feeling of continental interior. Dust, heat, large seasonal change, the kind of dryness that builds under vast skies. Monsoonal systems likely developed along margins, where seasonal heating and cooling pulled moisture inland and then let it retreat again. Mountain ranges redirected winds. Rain shadows formed. Wetlands clustered in favorable belts, while other regions baked. This is one reason the rise of reptiles mattered so much in this world. They were better suited than amphibians to expanding into drier environments. Eggs sheltered from drying. Skin less tied to constant moisture. Bodies increasingly capable of handling landscapes away from standing water. Amphibians still occupied important ecological roles, especially in wetter settings. But reptiles were beginning to exploit the full breadth of the assembled continent. Dimetrodon and other early synapsids, not dinosaurs, but strange predecessors on the mammal line, moved through parts of this world with sail-backed silhouettes that still look faintly unreal. Other reptilian lineages spread through dunes, floodplains, forests, and uplands. The land was not just joined, it was ecologically opening. But before we settle too comfortably into the grandeur of assembly, it is worth remembering that the path toward Pangea and the ages surrounding it were also shaped by visitors from outside the Earth. Asteroids and comets have always been part of the planet's story. We tend to reserve cosmic impacts for the dinosaurs because one later event is so famous, but the older Earth knew such visitors too. Some impacts were regional. Some were vast. Many scars have been erased by erosion, metamorphism, and plate tectonics. Yet enough remain to remind us that Earth has never evolved in perfect isolation. Take the Vredefort impact in South Africa, about 2 billion years old. It predates forests, animals, and everything we have been walking beside in recent parts of this story. Yet it left a scar of staggering scale. The Sudbury impact, younger, though still immensely ancient, altered crust and created mineral deposits that humans would someday mine. These were not merely fireworks in the sky. They were geological interventions, capable of melting rock, altering atmosphere and climate temporarily, and rearranging the opportunities available to life. By the Paleozoic, when marine ecosystems were rich and land life increasingly ambitious, impacts still occurred. Many were smaller than the giants of the earliest record, but even moderate impacts could be regionally devastating. More than that, some intervals may have experienced increased bombardment from asteroid debris, adding stress to ecosystems already strained by climate change. Sea level fluctuations, or tectonic reorganizations. Mass extinctions rarely have only one cause. The planet prefers complexity, even in disaster. Around the Ordovician, for instance, Earth may have passed through a period of increased meteorite delivery related to collisions in the asteroid belt. Some researchers have suggested links between bombardment and ecological change. During the late Devonian, when reefs collapsed and many marine groups suffered, impacts may have contributed alongside ocean anoxia and climate instability. It is debated, as so much in deep time is, but that uncertainty does not weaken the larger truth. The biosphere evolved under more than one kind of pressure. The sky sometimes struck back. Imagine one of those events in an age before birds, before cities, before anyone could name a star. A bright point grows too fast in the heavens. The air itself becomes a weapon. Shock waves move faster than comprehension. Dust rises. Seas recoil. Fires spread. Chemistry shifts. Then afterward there is silence, ash, and the slow legal work of survival. Life begins sorting itself again. deciding what remains possible. There is something almost unfairly dramatic about this, as if wandering continents, changing atmospheres, glaciations, forests, giant insects, and marine revolutions were not enough. The cosmos occasionally insisted on a guest appearance. Still, Earth absorbed those blows the way it absorbs so many internal convulsions, by changing. And then the continents continued their long convergence anyway. That may be the deepest lesson of tectonics. Even catastrophe rarely interrupts the larger rhythm for long. Oceans keep closing. Mantle currents keep pushing. The supercontinent cycle does not stop to grieve. It simply incorporates whatever has happened and continues. By the time Pangea was assembled, the Earth had become both more familiar and more alien. Familiar because the land now supported forests, rivers, reptiles, amphibians, insects, and landscapes with a texture we might partly recognize. Alien because the scale of unity was unlike anything in our lived experience. One immense continent. One great world ocean. Vast, dry interiors. Climatic extremes amplified by size. A planetary arrangement that felt complete and temporary at the same time. You know that feeling when you tidy your room too thoroughly, and for a moment, it looks almost staged. Almost like it cannot stay this way because life will inevitably move through it again. Pangea has always given me a little of that feeling. Too gathered. Too singular. Too much of the Earth in one place to remain untouched by the forces below. And of course it did not remain. Even at its height, the seeds of breaking already existed. A supercontinent insulates the mantle beneath it. Heat builds. The crust weakens. Rifts begin as fractures, then deepen into wounds, then become new ocean basins. The very success of assembly prepares the conditions for dispersal. That is the hidden irony in all supercontinents. Their completion contains the beginning of their end. But before that end, Pangea mattered deeply. It reorganized life. It changed marine shelves by reducing coastal areas in some places. It shaped interior dryness and equatorial wet belts. It provided corridors across connected lands that allowed faunas once separated by oceans to encounter one another. It prepared the stage for the Permian world, with all its strange synapsids and reptilian experiments, and eventually for the Mesozoic world that would follow after unimaginable losses. When we tell the story of continents joining, it is tempting to make it abstract. Plates, sutures, orogenes, basins, useful words, all of them. But beneath those terms is a more intimate reality. The ground moved. The sky changed with it. Life kept adjusting. Deserts spread where seas had been. Mountains rose where nothing once interrupted the horizon. Rivers found new paths. Forest belts shifted. Creatures expanded or retreated, survived or failed. Every tectonic event touched the living world eventually. So the road to Pangea was not only a geological march, it was a long preparation of settings, climates, and corridors. It gathered the stage and changed the cast at the same time. It brought old worlds together and quietly erased others. And perhaps that is why the final image of assembly feels so haunting, because it is both majestic and doomed. A continent made from the patient union of countless older fragments, each carrying memories of Rodinia, Nuna, Kenorland, and even older proto-continental seeds. Ancient crust fitted against ancient crust, mountains sown where oceans died. Life spread across the joined land in all its experimental confidence. Yet the deeper law remained in place. Nothing on Earth stays assembled forever. Still, for a while, the world wore that face. Pangea held together. Winds moved over its deserts. Forests gathered where rain permitted. Reptiles crossed landscapes no later creature would ever see in the same form. The coasts curved around a single immense body of land. The supercontinent had arrived, and once it had, the only possible next step was the oldest one of all. Change again. A fresh rearrangement. Another face for the planet. And another reminder that every map is temporary. When we think of the world, we usually think in the present tense. The continents are here. The oceans are here. The sky is blue. The forests are green. The ground seems dependable underfoot. Even when we speak of change, we often mean weather, seasons, a coastline shifting a little after a storm. Deep time asks something harder of us. It asks us to loosen our grip on the present and see it for what it really is. One arrangement among many. Before Pangea, there were other worlds, and not in the romantic sense of lost kingdoms or vanished civilizations, but in the truer and stranger sense of entire planetary faces. Nuna was a world. Rodinia was a world. Kenorland was a world. The tiny early cratonic seed, sometimes called belonged to a world so old and so altered by time that even calling it by name feels almost like an act of tenderness toward a thing barely preserved. Each of these Earths had its own arrangement of land and sea, its own climates, its own chemistry, its own opportunities for life. That is what makes the story so calming to me. Oddly enough, Earth has never needed to look the same in order to remain itself. There is comfort in that. Also a little unease, if we are being honest. Because permanence is one of our favorite illusions. We love the idea that maps are facts instead of snapshots, that mountains are forever instead of delayed erosion, that oceans are stable instead of temporary basins waiting for closure. The old Earth removes that comfort very gently. It does not shout. It simply shows you another version of home and waits for you to notice how unlike home it is. Think back through what we have wandered. A young planet with sparse continental crust and vast oceans under strange atmospheric haze. Tiny proto-continents surviving against the hotter restlessness of an early Earth. Kenorland assembled in a world where microbial life was reshaping the atmosphere, and oxygen was becoming both poison and promise. Nuna gathered ancient cratons into one of the earliest recognizable supercontinents. A broad, quiet stage under skies still unfamiliar to modern lungs. Rodinia formed and later broke apart. Its fragmentation, perhaps helping push the Earth toward global glaciations so severe they still feel almost fictional. Then the long rise of complex life, the spread of forests, the age of giant insects, the slow construction of terrestrial ecosystems, and at last the gathering that became Pangea. All of it real, all of it temporary. What strikes me most is how often the planet's great changes came from ordinary persistence rather than singular miracles. Microbes released oxygen one cell at a time. Tiny plants hugged wet rock and slowly turned continents green. Rivers kept carrying sediment. Roots kept breaking stone. Continents moved not in leaps, but in patient increments. Even mass extinctions, dramatic as they were, usually emerged from systems leaning too far for too long. Ocean chemistry, climate, volcanism, impacts, all layering stress until living worlds gave way. Earth history is full of cataclysm. Yes, but its deepest force is repetition. Continents gather, insulate the mantle beneath them, crack apart, and drift again. Oceans open and close. Carbon dioxide rises and falls. Ice advances, retreats, and returns in another age under other circumstances. Life expands, stumbles, rebuilds. The world does not follow a straight line toward anything. It moves in cycles, feedbacks, experiments, collapses, and recoveries. Honestly, I think that is why the old Earth feels so much more alive than the polished diagrams we were shown in school. The diagrams freeze everything. They offer labels and arrows and neat coastlines. Deep time is not neat. It is a breathing thing. It is a globe with a memory longer than any animal mind could hold. And still, despite all the change, there is continuity. The rocks beneath modern continents carry fragments of vanished assemblies. Ancient cratons lie buried under younger mountain belts and sedimentary cover. The oxygen in our air owes something to microbial labor in worlds before animals. Coal formed from forests that no human eye ever saw. Mountain chains preserve the sutures of dead oceans. The bones of present geography are stitched from older geographies. Even our own bodies carry this continuity. The vertebrate plan traces back through fish in Paleozoic seas. Our limbs echo fins. Our lungs belong to a lineage that once negotiated shallow waters and muddy shorelines. The soil under a forest path today exists because earlier plants made soil a planetary force. You could say, without too much poetry and with a good deal of truth, that we are walking on accumulated former worlds. I like to picture the Earth almost as an actor changing costume behind a curtain that never fully closes. One face recedes. Another appears. A methane haze becomes a blue sky. A barren coast becomes a forest. A vanished sea becomes a mountain belt. A swamp becomes coal. A desert interior becomes a future seafloor. Then the actor changes again. New costume, new setting, same underlying presence. And because the story never really stops, the future is already waiting in the present. The Atlantic is still opening. The Pacific is still being consumed around many of its edges. Africa is pressing north. Australia continues toward Asia. California slides slowly along its fault-bound path. Ice will come and go again. Carbon cycles will continue to answer the movement of rocks and the metabolism of life. Given enough time, another supercontinent will form. Some call it Pangea Proxima. Others propose different names and slightly different geometries. The exact arrangement remains debated. Because the future, like the ancient past, prefers not to sit still for sketches. But the broad truth is secure. The continents are not done. They were never done. Millions of years from now, coastlines that define our mental world will be gone. New mountains will rise from collisions that have not happened yet. Some oceans will close. Others will spread where none exist now. Creatures, if life remains rich and adapting, will inherit a planet whose map would look to us as strange as Rodinia or Nuna once did. Perhaps someone, or something, will look at rocks then and try to reconstruct our world the way we reconstruct those before Pangea. They will find traces, chemical whispers, magnetic signatures in minerals, fossils, sedimentary clues. They will piece together our arrangement and call it ancient. There is something wonderfully humbling in that. Human history feels large because it is our scale. Entire empires come and go in less time than it takes a continent to move a few kilometers. Languages flourish and vanish, while mountain belts continue the same slow erosion. A city may feel permanent to the people inside it, but deep time barely registers its existence. That is not an insult to our significance. It is a correction to our proportions. And perhaps proportion is one of the gifts of this story. When you hold enough time in mind, panic softens a little. Not because suffering is unreal, but because the world itself has always been in motion. Change is not evidence that something has gone wrong with Earth. Change is how Earth exists. The old faces of the planet tell us that instability and continuity are not opposites. They are partners. The planet remains by changing. Of course, life does not survive every change equally well. Mass extinctions were real. Entire lineages vanished. Trilobites, placoderms, giant carboniferous arthropods, reef systems, forest assemblage. So many once successful forms dissolved into fossil memory. The story is not sentimental. It does not promise that all things endure. It promises only that life keeps trying, that evolution keeps improvising, that after ice and fire and impact and flood, basalt and continental collision, some living thread usually remains to begin again. That thread ran through microbial mats, through cyanobacteria, through the first eukaryotic cells, through the first multicellular organisms, through fishes, forests, amphibians, reptiles, synapsids, mammals, and us. Not a ladder, never a ladder. More like a long braided river, crossing changing terrain, dividing, rejoining, drying out in one channel, surging in another. If you were standing here with me, by the low fire, after such a journey through old Earths, I think we would both be quiet for a minute. Not because there is nothing left to say, but because the scale of it asks for silence before words. The continents beneath us are older and more traveled than they appear. The air around us has been negotiated by ancient life. The map in our minds is only a temporary arrangement of drifting crust. Even the stars above, though steadier than coastlines, are being viewed through an atmosphere with its own immense history. And, still, this present world is not less beautiful for being temporary. It may be more beautiful. The Atlantic is more moving once you know it is young compared to older vanished oceans. A mountain is more impressive when you remember. It may contain the compressed memory of a dead seafloor. A forest path feels richer when you know how long it took for land to learn how to wear green. The modern Earth is not diminished by deep time. It is deepened by it. That may be the gentlest ending to all of this. Before Pangea, there was no empty preface. There was drama, ice, heat, microbes, strange skies, continental seeds, supercontinents, vanished oceans, early forests, giant arthropods, and the long patient making of the conditions that would later support more familiar worlds. Pangea was not the beginning. It was only one more face. Our present world is not the end. It is only another. So when you picture the Earth now, maybe do not see it as fixed. See it as paused, mid-movement. Continents caught in the middle of a slow dance. Oceans temporarily open. Mountains temporarily high. Forests temporarily rooted. Us temporarily aware of it. And maybe let that thought settle rather than disturb you. The planet beneath you has survived being many planets at once in character, chemistry, and climate, while remaining one world all along. It has worn deserts and ice, methane haze and oxygen blue, reefs and swamp forests, giant continents and scattered islands. It has lost faces and made new ones without ever running out of Earth. The fire is lower now. The room is quieter. Somewhere outside, on crust that has crossed impossible distances over impossible spans, the night goes on. The continents are still drifting, though you cannot feel it. The map is already aging. The oceans are already rehearsing future closures. The mountains are already softening grain by grain. The story continues without hurry. And that, more than anything, is what the worlds before Pangea leave with us. Not a single vanished paradise. Not a moral lesson carved neatly into stone. Just the deep, patient truth that Earth has always been changing, always been becoming, and somehow, through all those rearrangements, has remained home. Good night.